All right, so we're going to do some more modeling today with some variation. We'll make some equations from data points. We'll do some regression. We'll write equations with direct variation. We'll do inverse variation. We'll also do both, a combination, which we'll call joint variation. It's all stuff you've done before. All right, so let's try an example then of just modeling with regression. So what I want you to do is take this, plug this in L1, plug this in L2 in your calculator, do stat calculate linear regression, and try to get a line that models this data. Right? You should get this line right here, so see if you can do it. Okay, so what you want to do in your calculator is you want to go to stat, and you want to go to edit, and in L1 you want to enter in these years. I started with 0 as 2000, and then year 1 would be 2001, and so on. And then put the y values into L2. Then you go to stat calculate, and you want to do linear regression because we're doing a line here. L1 and L2, make sure L1 corresponds with x, and make sure your values that are in L2 will be your y values. Then I store the regression equation. I always store the regression equation in y variable, function, y1, because that way it puts it into my y equals, so that way I can look at the graph. And how you look at the graph is you turn your plot on, so that'll graph these points that you plugged into L1, L2. The line will be entered into Y1 because I did stat calculate and put the line in there. So now all I have to do is look at the graph. Now your graph might not show up at first because you're going to need to change the window. So what you need to do is go to Window and go to Zoom and do Zoom Stat 9. If you do Zoom Stat, it'll fit your window to your data points and your regression line. So what you'll see then is this. You'll have your data points that has graphed and the linear regression model that goes through those points. Okay? So this was the line, approximately. And that's exactly what we got. And it says, the last question is, how closely does that model represent the data? So to answer that, what you need to do is turn your diagnostic on your calculator. So go to Second Catalog and scroll down to D, diagnostic, and it should be in alpha mode. So you should just be able to hit D, and it'll go down to D's, and then scroll down to diagnostic. We want diagnostic on. Okay, hit diagnostic on, hit enter, and it says done. Now when you go to stat calculate linear regression, you can, when you hit calculate, it'll give you this R value at the bottom. So it gives me the A and the B, but it also gives me an R value. And basically, the closer that R value is to 1, the more appropriate this would be for a linear model that matches the data set. So basically, this tells us how good our line of best fit actually fits the data. The closer this is to 1, the better it fits the data. So that it's telling us that this data has a positive linear correlation because it's a number very close to 1. Some data is obviously not linear. Obviously, if the data goes like this, the data is more quadratic. And so a line isn't going to have, our R value won't be very close to 1. It's not a very good fit. But this data turns out that it's pretty linear, as we saw from our graph. Yep, so you could say this data models a linear relationship closely. How closely does the model represent the data? Our model right here represents the data very closely with an R value of 0.999. Here we go. All right, let's talk again about direct variation then. Here, first of all, a line, it has this general form with it's in slope intercept, which is y equals mx plus b. Okay, we could simplify this and call it direct variation if we get rid of the y-intercept. In which case, we won't use m for slope, we'll use k for slope. This is direct variation. It means that as x gets bigger, y also gets bigger, right? By some factor, and we can figure out whatever k is, but it's the constant of variation. That's what we're going to call it. Okay? So we can say that in direct variation that y varies directly as x, y is directly proportional to x, y equals kx for some constant k. And we're going to call k the constant variation, or the constant of proportionality. All right, so let's try an example then. In Pennsylvania, the state income tax is directly proportional to the gross income. Let's write an equation for this. It says you are working in Pennsylvania. Your state income tax deduction is $46.05 for the gross monthly income of $1,500. Find the mathematical model that gives us the income tax in terms of gross income. Go ahead and try this. Okay, so if you're going to do this one, it's y equals kx, right? Well, in this case, it says your state income tax. It says the state income tax, which I'll use I for, is directly proportional. So directly proportional to the gross income, which I'll use G for. Okay, so here's going to be our equation. Now it gives us 1 point. It gives us an income. State income tax deduction of 4605, and it gives us the gross income that we make that year is 1500. So we can then find what our K value is. We can then find our interest rate, so to speak. So divide both sides by 1560, or 1500. I'm sorry, 1500. And we get K to be 0.0307. That's 3.07% interest. So basically, of your income, 3.07% interest can be paid in tax. We can then write our equation as this: 0.0307 times G. So here's our direct variation equation that they're looking for, a mathematical model that gives us the state income tax in terms of gross income. Okay, we're also going to do some of these direct variation with an nth power. So we're going to say y varies directly with the nth power of x. Okay, we're going to say y is directly proportional to the nth power of x sometimes. These are going to be interchangeable. And then the equation will look like this. So y equals kx to the nth power. All right, here's an example. The distance a ball rolls down the plane is directly proportional to the square of the time it rolls. Okay, and it tells us at 1 point, it says during the first second the ball rolls 8 feet. All right, we can write an equation, and we can determine how far the ball will roll after the first 3 seconds. So why don't you guys go ahead and try this one real quick? Maybe pause it. Okay, so the distance the ball rolls down the ramp, this is like y equals kx squared. So we're going to use d for distance equals k x squared, where x is going to be time. So I'll just use t squared. So t for x and d for distance. T for time, d for distance. So they give us 1 point then. They say in the first second it rolls 8 feet. So I'm going to plug in 8 for distance, and I'm plugging in 1 for time. And that just gives me k equals 8. So my equation becomes d equals 8t squared. And then we can answer the question how far the ball rolls in 3 seconds by just plugging in 3 now for t. So you get 8 times 3 squared, which is 9. 9 times 8 is 72. So it would be 72 feet. All right. Next is inverse variation. We're going to say that y varies inversely with x, and that's going to be this equation here, where the bigger x gets, the smaller y gets. All right. We can also do y equals k over x to the nth power, so we can vary inversely with the square of the distance or something like that, in which case n would be 2. So let's take a look at one of those. Let's do this example. A gas law states that the volume of an enclosed gas varies directly with the temperature and inversely with the pressure. So this is going to be direct and inverse variation put together. All right, they give us a point. They say the pressure of the gas is 0.75 kilograms per square centimeter when the temperature is 294 Kelvin, and the volume is 800. All right, so let's write an equation, and let's find the pressure. Go ahead and try this. All right, so the volume, it varies directly with the pressure and inversely with the temperature. So this is the equation we're going to write. And then they give us 1 point. So we can find k with that 1 point. They say the volume is 0.75. When the pressure, the pressure is 0.75. The temperature is 294. And the volume is 8,000. We can go ahead and use that to find k, in which case you should get k. So we get 3,136,000 for k. So our equation is volume equals this constant, times the pressure over the temperature. And now we can find the pressure when the temperature is 300 and the volume is 7,000, for example. Just plug it in. And go ahead and solve for P now. And you get 0.669. And the units on that pressure was kilograms per square centimeter. Last is joint variation. Joint variation, we're going to say Z varies jointly with X and Y, for example. We can use this equation. And then, once again, we're going to have a constant variation K, which we're going to need to find. So we can have powers on each of these as well. Let's just try an example then. Simple interest for savings is jointly proportional to the time and the principal. So we're write an equation for that, and then after 1/4 we have a point. The principal is 5,000, and the interest would be 43.75. So let's find the interest after 3/4 then. All right. So simple interest is jointly proportional to the time and the principal. I'm going to write this equation. The interest in the principal is 5,000 is 43 after 1/4, 3 months. The interest is 43.75, so we'll plug that in for interest. The time is 3 months, and the principal is 5,000. All right. Let's then solve for K. Divide both sides by this. All right, so we get 0.0029. We can plug that back in for K, leaving I, T, and P as variables. But then it wants to find the interest after 3/4. 3/4 is 9 months. We're going to plug in 9 months for the time. And the principal is still 5,000. And let's find that corresponding interest rate, which gives us $131.25. Okay. Let's try some practice problems from the homework then, and we'll make a homework help video as well.